Hi everyone. So today we have seen a lot of data set related to brain and TBI, traumatic brain injury. So what we will be going through in this session is how we can use the data set to train a model and predict our own masks or annotations or segmentation, whatever you want to call it, and we're going to see how good a model performs as compared to someone creating a segmentation by their hand or as compared to what a radiologist would see. So I have worked with this framework, which is called MONAI. It's an open source medical imaging AI framework, which is built on top of PyTorch. So this was created by NVIDIA and King's College London, and it's all open source. You can go to the GitHub, and they have all sorts of code that you can run for your own data set. So I tested this framework for my own data set, which is a TBI data set, a traumatic brain injury data set for brain. So I'm going to share with you guys some preliminary results that I got by training my own model using MONAI. So we've already gone over this. The data set that I'm going to be working with is CT scans, and these are 3D images. And the challenges with 3D scans are they don't have as good of a resolution as an MRI would have. So it's a little bit tougher to train a model on images who are not very well, uh, who just don't have that much of a good quality. So that's what we're working with in Monai. A 3D. This is what a usual, like a typical 3D segmentation pipeline would look like. We start with the data, and it can be in Nifty or DICOM format. Um, we have some data loaders which gonna read and load our data, do some data augmentation, and then we pre-process our data. And this is all done through Monai, which is like written in Python, and all the resampling, normalization, scaling, cropping, everything comes under data preprocessing. And after we preprocess our data, it is now ready to be trained. So we start with, let's say we have 50 patients who have ranging anywhere from, like, let's say 1 ml to 400 ml of hemorrhaging, like blood, in their, like, brain injury. And what we have is annotation along with that. So what I mean by annotation is, like, it'll be the the region of interest in the brain where the injury has happened and where the blood is pooled. So we have our model and we have our annotations, labels created, and we feed that to the model, and we train the data. We train the model so that when we give it a data set which doesn't have any label or any masks, it will create a masks for us. So basically, the model will tell us where the region of interest is, and it's going to tell us what the volume of the blood is in that region of interest. So we have our model, we train it, and then we evaluate it using some metrics, um, and that's what we're going to see next. So this is what a very raw image of a brain would look like. And as you can see, there's not much you can see. There's, like, very lightly you can see there's, like, some whiteness around here, but an untrained eye definitely cannot see that. So we do some processing on over this data, and then this is a raw label that has been created by hand. Ideally, it should be created by someone trained under a radiologist or a neurosurgeon so that you know what you're doing, because your model is only as good as your data. So if your annotations are not good, if your labels are not good, then your model will not be able to predict uh, accurately. So we start off with this, and um, I'll slightly touch on what we've already talked about this Hounsfield scale reference. So this is just a scale of density of various regions in your, like for example, your brain. Water is going to be 0, the blood is about 30 to 45, and so on and so forth. So we're going to utilize this to train our model. Now, using MONAI, when we have done all our pre-processing, we have set the contrast. So this is the same image as this one, it's just flipped. After all the pre-processing that we have done, now you can actually see like this is the region of interest, and this is our masks that we created. And now we can actually give this to the model architecture and tell it to train itself. So we have done a lot of pre-processing on this, then which we'll talk about. So these are the different kind of transformations that I've applied on the data. We're loading our image and making sure it's in Nifty format. We are also making sure that the the channel is considered first. So for example, what I mean by channel is, for this label, you need to tell your model how many channels you have. So for this label, it's going to be 2. So 0 is going to be a background, and then 1 is going to be this region of interest. Sometimes you can have more than 2 channels. For example, let's say let's say, for example, brain tumor. You would want to not only like focus on your region of interest, but you would also want to see, okay, so this is my, let's say this is my core of model, the core of the tumor, and this is the outer region, like outer region of my tumor. So you can have multiple classes, but for this one, we're only going to go with 2, the background and the foreground. So yeah, I'm going to ensure that my channel is considered like converted for pre-processing. I'm orienting my data set. I'm also, making sure the intensity is proper. So for my model and my architecture that I chose, according to the Hounsfield scale unit, I went with a minimum of 0 and maximum of 100, which gave me the best contrast. So that's what I fed to the model, and I did some other transformations as well. So moving on, this is basically what it's going to look like. So we have our pre-processing. It's a 3D CD image. I have my slices, and I did some transformation. This is the manual label that I gave it. This is the raw data image that I gave it, and now I feed it to my segmentation model. So a segmentation model is something that which is actually doing all the work. So this is kind of a, like, this is the place where you need to understand very well the kind of model you're choosing and why you're choosing it, and how you're going to train it. So I'm going to give it to my segmentation model. In my case, I chose a unit model because unit model is like it's kind of like the backbone of segmentation. It started out with the 2D image, and over time, we developed like a 3D unit model, which I'm going to be working with. So we'll see in more detail what a 3D unit model is. So after I've given it to my model, what the output that I get is, for the slices that I gave it, this is the manual label, and this is what the model predicted by itself. So when I test my model on some training images, without giving it my ground truth, I'm going to compare it to how well it performed. And for this one, as you can see, like it looks pretty close to what the ground truth was. So yeah, talking about unit models, unit model has, like, this architecture has a lot of real world use cases. These are some of them. It started out with medical imaging, but then span like out in different use cases such as photo editing, self-driving cars, for example, Tesla FSD, satellite imaging, AR filters, motion tracking, and whatnot. So it has a lot of use cases. For example, let's say this is an example of motion tracking and segmentation. So we have a car and which is driving, and we're basically trying to segment like different parts of this moving video. So this is a GIF that I added. I don't know if this is working. Yeah. So what's a unit model? It's a unit. It's called unit because it's shaped like a U letter. Obviously, there are basically on a very like if at very fundamental level, it has two layers, which is an encoding, which is an encoder and a decoder. So the encoder, uh, what an encoder is doing is minimizing the amount of information at every layer and trying to understand what's in that image. So basically what I mean by that is starting out, we had this big input image. At every layer that we go down, it's gonna look at the image and try to figure out what area in this image can mean what. So for example, let's say this is a man on a bike. On the first layer, it'll only be able to understand that there's something vague over here which is different from the background. In the next layer, it will be able to tell, okay, so this is a man on a it's just a man over here, and in the next layer it'll be able to tell, okay, so this is a man, this is a bicycle, and in the background it's a house. So with every layer it starts to understand better what the image is, and this is our encoding part, um, and after encoding it builds back the masks that we get as an output from the segmentation. So it's gonna overlay the image with the mask that we provided it, and it's gonna see, okay, so this was the image, and I've detected the edges. I've detected that these are the pixels which can tell me that it's a cat or a dog or a man, and it gives us a segmentation map. So that's what a 3D unit model is. So in MONAI, this is how you provide build your architecture. I'm not going to go into a lot of detail on this one, but just give your dimensions. In channels is basically like we had just one image. Out channels is like, as I talked about, like we have a foreground and a background, and then among other things, the how good. So channels, and this over here is basically saying the number of filters that I'm going to apply at each level of encoding and decoding. So the more deeper the model gets, the more abstract it gets. So for example, we started off with 16. We can after 128, I could also add like 256, and it will go one more level deep and try to figure out what's happening in the image. So that's how we specify what unit model is going to look like. So after you train your model, how do you know how good it performed? These are some of the like plots and metrics that we can check after we train our model. I think the most well-known metric that we look for is the dice score. The higher the dice score, the better. For my preliminary data that I tested it on, I got it closer to like 0.7. So it's not the best model. The dice score is basically saying what is the difference between the ground truth and the predicted segmentation that the model created. So if the difference is huge, then your dice score is going to be low, and if there's very less difference between ground truth and what you got predicted, then it means your model is good. So basically, that's what dice score is. And just to show you a different picture, this was my region of interest. It's a hematoma. That was the ground truth that I provided. And after training, this is the output I got from my model. And this is just like a quantification of what the lesion volume is in ml. So my R score was like 0.98, so pretty close. The model performed, there wasn't a huge difference on the data set that I tested on. Like it was like 100 patients, and the volume of the lesion was anywhere from like 1 ml to 400 ml, and the relative volume difference between the ground truth and predicted was about 6 ml. So there was a 6 ml difference between both of those things. So yeah, this is predicted. I think that's about it. Some references, you can go to this GitHub and check out more MONAI tutorials. It's not the only model they have. They have like 3D segmentations, 2D segmentations, and uh, tons of different models that you can try out. So it's very, if you have like no deep learning experience, but you still want to train your own model, you can easily do so by going through the tutorials. So that's what I like about them. And yeah, you can connect with me. This is my email and LinkedIn. And yeah, any questions?